1.4. Study optimality of an algorithm. Optimality. Yeah. So in our first lecture here, I give you, several important things we need to do. So it's like an overview. Yeah. So these things we will work for the general algorithms discussion. Optimality is one problem. Sometimes we may need to discuss. Yeah. So in this unit, I use a simple example to explain this concept. Yeah. The problem number 3, find the minimum of an array. Minimum of an array. Okay? Yeah. Given an array, our data, here I do not say ordered or unordered. If I do not say that, you assume unordered. Right? Yeah. If ordered, you have to say it. If it is ordered, because that's a big information. You cannot miss that. Ordered. Yeah. If we do not mention anything, you assume unordered. Yeah. Find the index I such that A of I is the minimum of the array. That's simple. The question is very simple. I think the solution also very simple. You all know the solution, but the point is not about the solution. It's about optimality. Okay? We'll have a lot of discussion on optimality. All right? Yeah. The reference for this question, I put here. You can see 2 places. Yeah. Here you can see why I want to change the order. So when I rearrange the order, the way I save time, because this problem discussed in 2 places, 2 sections. So I do not need to discuss it twice, right? So I combine them. So I only discuss once to save time. Okay? Yeah. Otherwise, we don't have enough time for this class. Okay? We have to manage our time efficiently. Okay? Yeah. All right. Yeah. Problem type first. What problem type do we have here? Yeah. It's a selection type. We have one type of problems we call the selection problem. Yeah. So this is the one. Yeah. So what is the selection problem? So let me give you the selection problem description here. Find the kth smallest element in a given array. That's the selection problem. Kth element. Okay? Sometimes we call this kth smallest element has rank k. Rank k. Okay? Yeah. Another way to describe it. Yeah. So this is the general selection problem. And here our problem number 3 is a special case. Special case. In our problem 3 here, our k equals 1. The first smallest element. Okay? Later you will see we have many other selection problems. Okay? Yeah, we need to solve many other selection problems. For example, there is one big selection problem, most commonly used selection problem. Find the median. Find the median. You know the median, right? The rank in the middle. Yeah. For even number of elements, odd number of elements, how do we define the median? Okay? Find the median. That's the biggest selection problem. We will discuss later. Yeah. Because it's very complicated. Find the median. Okay. All right. The solution. Very easy for this one. Solution. So easy. Yeah. Right, yeah. So let's go through quickly. First, we do initialization. Right? We make our minimum variable min the first element of the array. Because at the end, we want this variable return the minimum element. Yeah. So the initial value is the first element. Then we go through the whole array. Okay? Yeah. General step. Compare min with a of I, the current element, ith element, or element with index I, current element. Okay? Two possibilities. Min greater than a of I. In that situation, we update the min variable, its value. We update its value. Yeah, we get a smaller element. Yeah. Otherwise, yeah, because otherwise that means min less than or equal to a of I. We do not change. Yeah. We go to the next element for comparison. Okay? After we compare min with all the elements, after the first one, yeah, the first one we don't need to do comparison, right? Yeah, first one it's an assignment. We don't do comparison. After that, we do all the comparisons. Okay? Until I equals, yeah, actually, after I equals, yeah, but because we need to do I equals m, we still need to, oh, sorry, yeah, because I plus 1, yeah, so I plus, out of the bound, yeah, when I, so until I equals, then we stop, right? We stop, yeah, because I equals n minus 1, you don't have this element, out of bound, yeah, until that. So we stop. Okay. All right. Finally, after you complete all the comparisons, you can return the minimum value. That's the simple solution. Okay? Yeah. Very easy. Yeah. But we need to discuss first, we need to look at its efficiency, right? Efficiency. Second, optimality. After we see the efficiency, then optimality. Okay? Yeah. Number of comparisons. Can you tell me the number of comparisons here? Based on my description, exact number. Okay? This time, don't give me the dominant term, right? Give me exact number. All right. As I said, we do not do comparison for the first element. After that, each element we need to do comparison, right? Yeah. Based on that, tell me the answer. N minus 1. N minus 1. Not n. Don't give me n. N minus 1. That's why I ask you for the exact number. 1 is important. Okay? Here. 1 is important. Yeah. All right. N minus 1. Okay? Now let me ask you, what is the best case? What is the worst case? What is the best case? What is the worst case for this algorithm? Right? Yes. Same thing, right? Best case also n minus 1. Worst case also n minus 1. No matter what that. So here, the best case, worst case means for different input. We apply this algorithm for all types of inputs. How many, the number of comparisons you need, best case, worst case. You need to do this many all the time. Okay? So the best case, worst case, average case, all this number. Right? Yeah, that's simple. Okay, that's simple. All right. But the main discussion is regarding the algorithm optimality. So at this point, we want to ask, is this algorithm optimal? Right? Yeah. Optimality, optimal? Right? Yeah. So let's have discussion on it. Yeah. Is it possible to further improve the algorithm? Yeah, because this question is related to this title question. Based on the answer, you can make your decision. If this algorithm is already optimal, can you improve it? Nobody can improve it because it is optimal. It is the best you can get. It is the best everyone can get. Okay? Including everyone in the world. It's optimal. Yeah. So no improvement anymore. Right? Yeah. If the algorithm is not optimal, then you have room to improve. Although it may not be easy, but there is a possibility to improve it. So that's why we need to answer that question. Otherwise, we need to consider if it is possible to further improve the algorithm. All right. Two options. First, it's possible. You need to improve. We need to improve. Okay. Second, impossible. Impossible. Yeah. But in that case, case number two, impossible, already optimal. In that case, you need to convince people that it is already optimal. That's not easy, right? You just say it is optimal, that's not very convincing. How do you explain it is optimal, right? Yeah. You need to really provide very strong, very convincing arguments. Here, we will do that. So, using this example, we will do that. The answer, this algorithm is optimal. It's optimal. Okay? But we need to convince people it is optimal. That's the hardest part. Okay? Yeah. Let's see how to do it. The hard part. Among all the possible algorithms, how do we interpret optimality? Right? Here, how do we interpret optimality among all the possible algorithms? How to show that this one is optimal? All the possible algorithms. You see this? This part, all the possible algorithms. Many of them, I don't know, how can anyone exhaust all the possible algorithms for this problem? Can anyone? Nobody can exhaust all possible algorithms. Many of them unknown. Right? Many of those possible algorithms are unknown. Okay? If the algorithm is unknown, how can you compare with it? Okay? How do you make some conclusion or make some argument regarding some unknown algorithms. That's the hard part. That's the hard part. We can do it. Okay. We can do it. Okay. In this simple example, let me show you how to do it. Explore properties. Property is important. Remember in our summary, the property. Explore properties. By exploring properties, you can make that convincing argument. Okay? Yeah. So property is important. Why property is so important here? Because even those unknown algorithms, remember, the hard part is how to deal with these unknown algorithms. Even for the unknown algorithms, they also have the same properties. We can find their properties. So we use those properties to make convincing argument. Let me show you how to do it here. All right. Convincing argument. Okay. Imagine the mean variable is the final winner. Yeah, because at the end, we return its value. So let's make some nice story of it. Okay. We use imagination. We make some nice story to help us thinking. Thinking, sometimes we need to use some nice story on it. Okay. Here, the winner. So it's like playing a game, right? So winner, loser. Yeah. Okay. When you do comparison, that's like a game, right? So one beats another one, right? But here, when we do comparison, the one with smaller value is the winner. Yeah? Because we want to find the minimum. The one with the smaller one will be the winner. Okay? So the minimum value means this one beats all the other elements in the array after all the comparisons. Okay? Yeah. Yeah. So let's use that simple story. Yeah. Because based on our experience in everyday life, we can understand that story. We can use that familiar story to help us thinking easily. Yeah. Right? Yeah. Good. Yeah. This minimum number needs to beat all the other elements in the array through comparisons directly or indirectly. Okay? So here I emphasize. Directly, that's easy. Right? We know you beat another element directly. We know that meaning. But what's indirectly? Okay? Yeah. Indirectly, that's also very common. We need to consider that situation. So here, let me give you the indirect beat. Indirect beat. Okay? All right. A less than B. Okay? A beats B based on our rule here, right? Yeah, the smaller one is the winner. Okay? All right. B beats the element C, suppose. B is less than. Okay? All right. Then A beats C, right? But for this one, do we need to do comparison? We don't need. Okay? We know A is smaller than C by transitive property, right? Transitivity property. Okay? This order relationship can be translated, okay? Yeah, like this. So after these two comparisons, we say A beats C indirectly, right? Yeah, because they never play any game, but we know A beats C. That's indirectly. Okay? So we also need to include this case indirectly. Yeah. Now, so let's do the next step. If an element loses once, it is eliminated, right? Yeah. Because if an element loses just once, it can never be the minimum, right? It can never be the minimum. Why we include it? Okay? So here we use another simple method called elimination method. We eliminate. If any element, any number element, if it cannot be the solution, we eliminate it from the consideration so we can simplify our data, right? After you eliminate it, your data is reduced. Okay? So it becomes simpler. Yeah. So this is the elimination method. So very simple, but very effective. Yeah. Here we use that. Okay. We eliminate that. Okay. All right. Next. Each comparison can only eliminate one element. So here you can see all these observations, they are properties, right? We explore properties for this problem. See? That's also an analysis step. Okay? Yeah. So next observation, each comparison can only eliminate one element. Can a comparison eliminate two elements? Right? So one element. Okay? Each comparison. Okay. Yeah. All right. We need to eliminate n minus 1 elements, right? Because at the end, only there is one winner. Okay? Only one player left. All the remaining n minus 1, all eliminated. Right? So in other words, if you want to eliminate n minus 1 players, how many games do you need to play? N minus 1. Because each game you can only eliminate one player. Right? You cannot eliminate two players in one game, right? Yeah. Each game only one player eliminated, but you need to eliminate n minus 1 total player. You need to play minimum n minus 1 games, right? Minimum. You cannot do fewer than n minus 1 games. Right? Fewer. That's not enough. Okay? Yeah. So that means you need at least n minus 1 comparisons, the minimum. Right? Even for unknown algorithms, right? Even for unknown algorithms, you need to make at least n minus 1 comparisons, right? Here you can see unknown algorithm, because we know their properties, so we can discuss about the unknown algorithms. Okay? Yeah? At least, right? No exception, right? No exception. That means this number, if we can reach this number, it's optimal, right? Yeah. Our solution has this performance. We have it. Our solution, we have this. That means our solution is optimal. Yeah. That's the convincing argument. Right? Convincing. Yeah. Yeah. If you do this argument, so then you never need to improve it. It is already optimal. Why you need to waste your time and money to improve it? Okay? Already optimal. Okay? Yeah. All right. So any question? All right. Yeah. That's our discussion for this class. Okay. Yeah. Next time we have 1 unit left for lecture 1. Unit number 5. Yeah. We will finish lecture 1. And we will start lecture 2 next time.